After Comet 3I Atlas passed its perihelion, astronomers around the world expected the usual behavior: brightening, the formation of a tail composed of dust particles and ionized gas, and then a gradual retreat from the Sun along its predicted orbit. But in late February, observational stations recorded something astonishing. The comet's trajectory had changed. Although it appeared outwardly as a typical comet with a diffuse nucleus and a faint tail, telescopes and radar data revealed that its orbit had deviated from the projected path. Few understood what this could mean, and perhaps no one was prepared for the scale of the consequences. Initially, astronomers assumed a simple outgassing effect. Comets consist of ice, dust, and gases, and when heated by the Sun, they actively sublimate, creating jets capable of slightly altering the object's velocity. However, calculations showed that the velocity change was too significant to be explained by gas outflow alone. This suggested an external influence. Speculations ranged from collisions with micrometeoroid streams to unknown gravitational interactions, or more fantastically, the presence of a large cosmic body hidden from observers. The astronomy community faced an unpredictable scenario. 3I Atlas began moving along an orbit that gradually approached the inner solar system at an angle unusual for comets of this type. If this scenario proved correct, the implications for planetary dynamics could be far-reaching. Scientists began running a series of models to predict the comet's future trajectory and potential risks for Earth and other celestial bodies. As the comet approached Mars's orbit, deep space cameras recorded an increase in brightness, indicating a sharp rise in outgassing. This produced new, unexpected tails, not only dust, but also gas. Spectral analysis revealed rare molecules previously observed only in the deep layers of the nucleus. This suggested that the orbital change caused internal mechanical stresses and fractures in the nucleus, exposing layers that had remained hidden until now. Among astronomers, a discussion emerged regarding the uniqueness of the event. Comets are known to follow predictable Keplerian laws, and small deviations are fairly common. But 3I Atlas demonstrated something qualitatively different: changes that could indicate internal instability of the nucleus or even unknown properties of interplanetary space it was traversing. Some scientists speculated that the nucleus might contain unstable compounds reacting with solar radiation with unexpected dynamics, effectively creating a natural engine capable of adjusting the orbit. Meanwhile, observational networks worldwide recorded unusual interactions of the comet's tail with the solar wind. Particles moved along curved paths, creating the effect of a true cosmic dance. Scientists explained this by the complex interaction between the Sun's magnetic field and charged particles in the tail. Photographs and videos from NASA and ESO telescopes showed glowing clouds of gas and dust twisting around the nucleus, giving the illusion of a living organism responding to external stimuli. At the same time, physicists calculated the potential impact of the new orbit on the planetary system. Even a small orbital shift can trigger a chain reaction, especially if the comet passes near Lagrange points or massive planets. Modeling showed that gravitational effects from Jupiter and Saturn could either stabilize the new orbit or amplify its deviation, creating a long-term risk for asteroid belt dynamics and even Earth's orbit. Scientists began exchanging hypotheses about the possible causes of such a radical orbital change. Some suggested this might be the first observed case of a natural gravitational lever, where the comet, passing through a cloud of invisible objects or weak fields, receives a significant impulse. Others argued it could be evidence of unknown cosmic processes capable of influencing bodies over vast distances, processes modern science cannot yet fully explain. International space agencies started preparing observation missions to study 3I Atlas in detail. Remote probes were proposed to analyze the nucleus, the chemical composition of the tail, and the magnetic field around the comet. The data was expected to clarify not only the nature of the anomaly, but also fundamental processes of comet formation and evolution within the solar system. As the comet approached its new orbit, the nucleus's brightness became unpredictable, and the tail exhibited complex fractal structures. Astronomers around the world observed the event in real time, discussing how unusual and potentially historic it had become. Many began asking, was this a warning that the solar system conceals mechanisms we still do not understand? Or was this a coincidental alignment of factors that would never recur? Gradually, an intrigue emerged. The orbital change of the comet could affect the future of space research and our understanding of interactions within the solar system. Observational data indicated that even small deviations could trigger complex cascading effects, influencing the motion of other objects. Astronomers began rethinking old dynamic models and incorporating new parameters previously considered negligible. As 3I Atlas moved beyond Jupiter's orbit, its trajectory became more stable, but scientists knew that this was only a temporary stabilization. Processes within the nucleus were unpredictable, and in the future, the comet might again alter its course. For science, this event served as a reminder that the solar system is not a static construct, but a dynamic and unpredictable environment, where even familiar objects can exhibit unexpected and astonishing changes. As 3I Atlas continued its journey beyond Jupiter, space agencies and observatories intensified monitoring efforts. High-resolution spectrographs revealed that the comet's composition was far more complex than previously assumed. Organic compounds were detected alongside volatile ices, including traces of molecular oxygen, a discovery that challenged established theories of comet formation. The uneven outgassing patterns suggested that the comet's internal structure was irregular, with pockets of trapped gases suddenly releasing under thermal stress. This sporadic activity contributed to the subtle changes in its trajectory, which initially seemed inexplicable. Meanwhile, orbital analysts developed sophisticated simulations to understand the long-term consequences of the deviation. The models demonstrated that even a slight alteration in velocity could translate into dramatically different paths over decades. In one simulation, the comet's orbit intersected the asteroid belt at a slightly steeper angle, potentially increasing collision probabilities with smaller bodies. Another model suggested a resonant interaction with Jupiter's gravity that could either stabilize the orbit for centuries or destabilize it, creating unpredictable interactions with inner planets over millennia. Astronomers were particularly concerned about the potential impact on Earth. Though immediate collision risks were negligible, the altered orbit meant that future perihelion passages might bring the comet closer to Earth than any previous encounter. This sparked debates in the scientific community regarding planetary defense strategies and the importance of long-term monitoring. Some researchers argued for enhanced observation networks, including space-based telescopes dedicated exclusively to tracking dynamically unstable comets. The comet's tail became a focal point of fascination. Unlike typical cometary tails, which align neatly along the solar wind vector, 3I Atlas exhibited bifurcated streams, one curving ahead of the nucleus and another trailing far behind. Detailed analysis revealed that these structures were shaped by complex electromagnetic interactions between ionized gas in the tail and the fluctuating solar magnetic field.
The phenomenon provided an unprecedented natural laboratory for studying solar-wind comet interactions, offering insights into plasma physics on a cosmic scale. As the months passed, international collaborations formed to conduct coordinated observations. Observatories in the southern hemisphere tracked the comet's nucleus, while northern facilities focused on its tail and plasma environment. Data shared in near real time allowed scientists to refine models of both the comet's orbit and the underlying physical processes driving its unexpected behavior. Graduate students and early career researchers found themselves participating in a real-time cosmic mystery, analyzing data streams that challenged decades-old assumptions. Simultaneously, theoretical physicists explored more speculative explanations for the orbital anomaly. Could there be unknown interactions with dark matter or other hidden mass distributions in the outer solar system? While such ideas remained controversial, they prompted the development of new instruments designed to detect subtle gravitational perturbations. The scientific community was witnessing a rare convergence: observational astronomy, computational modeling, and fundamental physics coming together around a single enigmatic object. One particularly intriguing discovery came from polarimetric studies of the dust in the comet's coma. The particles were highly irregular and exhibited unexpected reflective properties, suggesting a complex formation history. Scientists speculated that 3I Atlas might have originated from a region of the solar system far more distant than other known comets, preserving primitive materials from the earliest epochs of planetary formation. If true, this made the comet not only a subject of orbital intrigue, but a repository of primordial solar system chemistry. Even as the comet drifted farther into the outer solar system, its influence on scientific thinking remained profound. Researchers began revisiting historical observations of comets with unexplained orbital deviations, comparing them to the behavior of 3I Atlas. Patterns emerged that hinted at a broader class of dynamically unstable comets, previously overlooked due to observational limitations. This recognition prompted the establishment of a new research framework for understanding small bodies in the solar system, integrating long-term orbital monitoring with detailed compositional studies. Public interest also surged. Amateur astronomers shared stunning images of the comet's complex tails, while documentaries explored the broader implications of cosmic uncertainty, the realization that even objects following Keplerian paths can defy expectations, reminding humanity of its limited understanding of the universe. By the time 3I Atlas receded to the outer planets, it had already left a lasting mark on science. Not merely a comet, it had become a symbol of the unpredictable dynamics of the solar system. It challenged existing paradigms, expanded observational capabilities, and inspired new generations of astronomers, physicists, and engineers. Each dataset collected, each simulation run, contributed to a slowly emerging narrative that the solar system is a living, dynamic environment where even seemingly small changes can have far-reaching consequences.
As 3I Atlas continued its journey deeper into the solar system, astronomers began to model not only its trajectory, but also its potential influence on neighboring celestial bodies. Even though immediate threats to Earth were negligible, the comet's altered orbit introduced subtle gravitational perturbations in the asteroid belt. Over decades, simulations suggested that some smaller asteroids could experience slight shifts in their orbits, increasing collision probabilities with one another. While such events might take centuries to manifest, they offered a rare opportunity to observe the cascading effects of a single, dynamically unstable body. Planetary scientists were particularly intrigued by the possibility of long-term resonances between 3I and Atlas and the gas giants. Jupiter, with its immense gravitational influence, could act as both stabilizer and amplifier of the comet's motion. Models indicated that during specific alignments, the comet could gain or lose significant orbital energy,
potentially altering its perihelion distance by millions of kilometers. Saturn and Uranus, though less massive, also contributed subtle perturbations, creating a complex web of gravitational interactions. Researchers realized that even distant comets could not be treated as isolated objects. Their trajectories were entwined with the broader planetary system in ways previously underestimated. Meanwhile, the comet's chemical composition continued to fascinate spectroscopists. The discovery of volatile organics, rare ices, and previously unobserved molecular species suggested that 3I Atlas preserved material from the early solar system that had remained untouched for billions of years. Some hypothesized that studying these compounds could provide clues about the origin of water and organic molecules on Earth, connecting the comet's unpredictable orbit with fundamental questions of planetary formation and the emergence of life. Laboratory experiments simulated the conditions within the comet's nucleus, revealing that even slight changes in temperature or internal pressure could trigger rapid outgassing events. Such bursts, they concluded, might have contributed to the unexpected orbital shift after perihelion. In parallel, space agencies began exploring the feasibility of sending an intercept mission to 3I Atlas. While the comet's orbit was unusual, careful calculations suggested that a probe could rendezvous with it during a future perihelion passage. Mission planners envisioned a suite of instruments capable of mapping the nucleus in 3 dimensions, analyzing dust particle morphology, and measuring electromagnetic fields in situ. Such a mission promised unprecedented insight into cometary physics and the dynamics of small bodies in the outer solar system. The scientific community debated the mission's feasibility, costs, and potential scientific payoff, but consensus emerged. 3I Atlas represented a once-in-a-generation opportunity. As the comet receded beyond Saturn, remote sensing observations revealed that its activity continued, albeit at a lower level. Sporadic jets of gas and dust persisted, indicating that internal processes within the nucleus were ongoing. These emissions, though minor compared to perihelion activity, still influenced the comet's trajectory, demonstrating the persistent impact of internal dynamics on orbital evolution. Scientists noted that such behavior might help explain other historical cases of anomalous comet motion, prompting a re-evaluation of long-term predictions for many small bodies. The study of 3I Atlas also spurred advancements in computational modeling. Traditional N-body simulations, while accurate for most objects, struggled to account for the combined effects of internal outgassing, gravitational perturbations, and electromagnetic interactions. Teams of mathematicians and physicists collaborated to develop hybrid models, integrating fluid dynamics, plasma physics, and celestial mechanics. These models allowed researchers to simulate the comet's motion with unprecedented precision, revealing subtle feedback loops that could amplify or dampen orbital changes over decades. Public fascination with 3I Atlas grew alongside scientific interest. Planetarium shows, documentaries, and online interactive simulations brought the comet story to a global audience. People marveled at the notion that a small, icy body, traveling through the vastness of space, could subtly alter the architecture of the solar system. Educators used the comet as a teaching tool, illustrating principles of orbital mechanics, gravitational resonance, and the complex interplay between physical forces that govern celestial bodies. Despite the media attention, the scientific significance of 3I Atlas lay in its unpredictability. Unlike most comets which follow well-established orbital paths, 3I Atlas demonstrated that small deviations could accumulate over time, producing outcomes that are difficult to foresee. It challenged assumptions, prompting a re-evaluation of risk assessment models for cometary encounters. Long-term monitoring became essential, not only for understanding this comet, but for improving predictions for other dynamically unstable bodies that might pose a threat to Earth in the distant future. As years passed, data from 3I Atlas continued to arrive from telescopes around the globe. Each observation revealed new complexities in its structure and behavior, reinforcing the notion that comets are not merely inert ice balls, but dynamic, evolving systems. Scientists documented fractal patterns in the dust tail, variations in outgassing rates, and shifts in rotational axis orientation. The accumulated knowledge offered a window into processes that shaped the early solar system and provided a natural laboratory for studying the fundamental physics of small bodies under extreme conditions. By the time 3I Atlas approached the outer reaches of the Kuiper Belt, its legacy was firmly established. The comet had challenged assumptions, inspired innovative research, and connected multiple disciplines, from planetary science to plasma physics, from chemistry to computational modeling. Its journey reminded humanity that the cosmos is not static. It is a complex, dynamic environment where even the smallest bodies can have profound implications. In the annals of astronomy, 3I Atlas would be remembered not only as a comet with an unusual orbit, but as a symbol of the solar system's hidden dynamism and the enduring human quest to understand it.
As 3I Atlas ventured farther into the outer solar system, the enigma surrounding its orbital deviation refused to fade. Astronomers noted subtle, unexplained shifts in its trajectory that defied all conventional modeling. Each new observation seemed to reveal a hidden variable, an invisible hand altering the comet's path in ways that could not be entirely accounted for by known physical forces. Some researchers whispered of unknown interactions, perhaps a faint gravitational influence from a massive, unseen object beyond Neptune, or the presence of material yet undetected in the distant reaches of the Kuiper Belt. Theories multiplied, each more speculative than the last, feeding a quiet tension that reverberated through the global scientific community. As weeks turned into months, a deeper layer of intrigue emerged. The comet's outgassing patterns became increasingly irregular, sometimes producing jets on opposite sides of the nucleus simultaneously. These bursts of activity created tiny but measurable changes in momentum, suggesting that the comet's interior might be undergoing processes far more complex than simple sublimation. Polarimetric studies revealed fractures in the nucleus, and the distribution of dust and ice hinted at hidden cavities or channels, almost as if the comet were a fragile, self-adjusting system capable of reacting dynamically to external forces. No one could explain with certainty why these events intensified precisely after perihelion, leaving open the question, was 3I Atlas being influenced by an external force, or were its internal processes far stranger than previously imagined? The comet's unpredictable behavior sparked an unprecedented wave of collaboration among scientists worldwide. Teams of astronomers, physicists, and computational modelers pooled data to create hybrid simulations, yet even the most advanced models failed to capture the full complexity. The trajectory oscillated in subtle ways, as if resisting prediction. Each pass of the comet by a massive planet, each interaction with the solar wind, revealed new irregularities, creating a growing sense of unease. 3I Atlas was rewriting the rules of what a comet could do. Meanwhile, the implications for Earth and its neighboring planets became a subject of careful speculation. Even though no immediate threat existed, the possibility that 3I Atlas could, in centuries or millennia, approach the inner planets more closely than expected sparked debates among planetary defense teams. Could this comet, with its unpredictable internal dynamics, one day become a dangerous visitor? Or was it simply a cosmic anomaly, a one-off spectacle of nature's complexity?
Scientists argued over these questions, yet every answer seemed provisional, incomplete, feeding the narrative of uncertainty that hung over the comet like a shadow. The intrigue deepened when new chemical analyses revealed traces of elements and molecules never before observed in a comet's tail. Some of these substances suggested interactions with the solar magnetic field that were not fully understood, potentially creating forces capable of subtly altering the orbit. If verified, this would represent a mechanism of cometary motion entirely unknown, a process that could have operated silently in other small bodies throughout the solar system without ever being detected. The possibility that 3I Atlas held secrets about the unseen forces shaping planetary systems became a tantalizing scientific puzzle, drawing the eyes of researchers far beyond traditional astronomy. As 3I Atlas receded beyond Saturn, the comet's tail fragmented into multiple streams, shimmering faintly under the glare of distant sunlight. Each stream seemed to tell a story of past activity and hidden interior pressures. Scientists proposed that these patterns were like fingerprints of internal forces, each jet and outburst leaving an imprint on the comet's momentum. The more they studied, the more they realized how little they truly understood about the internal life of such bodies. Questions multiplied. Could the comet suddenly change direction again? Could it harbor mechanisms or structural features capable of triggering a dramatic orbital shift in the future? Even the public became aware of the mystery. Social media buzzed with images of the comet's fractal tails, while science communicators highlighted the unanswered questions. Why did 3I Atlas deviate after perihelion? What does this mean for our understanding of the solar system? Documentaries portrayed the comet not just as a celestial object, but as a cosmic detective story unfolding in real time, where every observation might reveal the next clue in a puzzle that no one could yet solve. In laboratories on Earth, researchers simulated conditions within the comet's nucleus. They tested how trapped gases, varying pressures, and extreme temperature changes could produce sudden jets capable of altering momentum. Yet even with controlled experiments, the scale and timing of 3I Atlas's orbital change remained largely unaccounted for. Some speculated about influences from interstellar space, unseen particles, weak gravitational anomalies, or subtle electromagnetic effects from the sun or distant planets. The comet, it seemed, was both a window into the early solar system and a mirror reflecting the limits of contemporary science. By the time 3I Atlas approached the outer edge of the Kuiper Belt, scientists had compiled years of data, each observation layered with questions rather than answers. The comet's behavior had rewritten expectations, creating a persistent tension. Would it continue its subtle, unpredictable shifts indefinitely? Could its next perihelion reveal further anomalies? And what might these behaviors imply about other comets, past, present, and future? In the quiet spaces between telescopic images and computational models, a narrative of cosmic intrigue had emerged, one that would keep scientists pondering, debating, and searching for answers for decades to come.
As decades passed, 3I Atlas remained under careful observation. Its unpredictable behavior continued to confound scientists, who realized that each new perihelion passage might hold revelations that could reshape our understanding of cometary physics. Computational models projected multiple possible futures for the comet. In some, it settled into a relatively stable orbit in the outer solar system. In others, slight changes in outgassing or gravitational nudges from Jupiter could send it on a trajectory that would bring it closer to the inner planets centuries from now. Every scenario carried uncertainty, and the mere possibility of a dramatic orbital shift kept researchers alert. Meanwhile, the comet's interior composition became the subject of intense speculation. Spectroscopic data hinted at layers of volatile ices interspersed with organic compounds, while irregular jets suggested hidden cavities where pressure could build over time.
Scientists wondered if these internal structures might function almost like natural mechanisms, capable of producing sudden impulses that could alter the orbit without any external cause. Could 3I Atlas harbor a self-regulating system, a cometary engine powered by its own internal chemistry? The idea seemed fantastical, yet each anomalous observation lent it a sliver of plausibility. In the outer reaches of the solar system, the comet's tail continued to evolve in ways that challenged conventional understanding. Streams of dust and gas occasionally appeared to curve ahead of the nucleus, moving in defiance of expected solar-wind interactions. These patterns suggested electromagnetic forces at play on a scale previously unimagined, raising questions about the broader influence of the Sun's magnetic field on distant icy bodies. Some researchers began to hypothesize that other comets, long considered passive, might harbor similar hidden dynamics, waiting to reveal themselves under the right conditions. Humanity's curiosity did not go unanswered. International space agencies developed plans for a probe capable of intercepting 3I Atlas during a future perihelion passage. The mission would aim to measure its internal structure, map the cavities that might be responsible for anomalous jets, and analyze the unique molecular compounds preserved since the birth of the solar system. Engineering teams grappled with the challenges of navigating an object whose orbit defied precise prediction, and every calculation carried an element of uncertainty. The comet itself seemed almost aware of human curiosity, revealing new mysteries just as mission plans solidified, keeping scientists in a perpetual state of anticipation. Meanwhile, theoretical physicists explored even more extraordinary possibilities. Could the comet's unexpected behavior be influenced by faint gravitational waves, dark matter filaments, or other interstellar phenomena interacting with its mass? While highly speculative, these ideas were grounded in careful analysis of orbital deviations that could not otherwise be explained. 3I Atlas had become not only a subject of observational astronomy, but also a portal into fundamental physics, where the known laws were tested against a singular, enigmatic example. Public fascination with the comet grew alongside scientific intrigue. Images of its fragmented tail, glowing streams of gas and dust, and sudden bursts of activity captured imaginations worldwide. Documentaries framed it as a cosmic mystery unfolding in real time, a puzzle that scientists, educators, and enthusiasts could all follow, layer by layer, with each new observation revealing only more questions. Headlines speculated wildly, reflecting both the excitement and unease that 3I Atlas had inspired. As 3I Atlas approached the fringes of the Kuiper Belt, the tension remained unresolved. Could it maintain its current orbit, or would an internal outburst or gravitational encounter once again alter its path? Could its unexpected behavior be a harbinger, hinting at unknown forces acting upon the solar system's small bodies? Each calculation, each observation, each simulation added new data, but also new uncertainty. The comet's journey had become a living demonstration of cosmic unpredictability, a narrative threaded with intrigue that challenged the very limits of scientific understanding. Even in the quiet of the observatories, where telescopes scanned the dark, distant reaches of space, the comet's presence was palpable. It was a reminder that the universe is never static, that even familiar patterns can be disrupted by subtle forces, and that our understanding, no matter how advanced, is always provisional. 3I Atlas, with its altered orbit and mysterious internal dynamics, had become a symbol of the unknown, a celestial enigma whose full story would unfold only with patience, persistence, and perhaps centuries of careful observation. And so the comet traveled onward, silently, inexorably, its path uncertain, its secrets intact, leaving scientists, students, and the world at large to wonder what truly caused 3I Atlas to change course, and what other mysteries might the solar system still be hiding.
Over the following decades, 3I Atlas continued its journey into the distant reaches of the solar system, yet its story remained far from complete. Observational data accumulated layer by layer, revealing subtle changes in the comet's trajectory, variations in outgassing, and unexpected rotations of its nucleus. Each discovery reinforced the central mystery. The initial orbital deviation after perihelion had not been an isolated event, but rather the opening chapter in an ongoing saga of unpredictable cosmic dynamics. Scientists began to consider that perhaps 3I Atlas represented a new class of cometary behavior, bodies capable of self-modifying their motion through intricate internal processes, interactions with the solar magnetic field, and hidden gravitational influences. Space agencies continued to plan ambitious missions. A fleet of remote probes was proposed, each designed to intercept the comet at strategic points along its orbit, to map internal cavities, analyze volatile compounds, and measure minute electromagnetic effects. These missions required unprecedented precision, as the comet's unpredictable momentum meant that even a small miscalculation could result in a missed rendezvous. The comet seemed to taunt humanity with its uncertainty, revealing new layers of mystery just as engineering plans approached finalization. Meanwhile, theoretical physicists pursued more radical hypotheses. Some suggested that 3I Atlas might serve as a natural laboratory for observing the subtle effects of interstellar phenomena on small bodies. Could faint gravitational waves, dark matter concentrations, or interstellar plasma flows be subtly influencing the comet's orbit? Each new hypothesis carried profound implications. If true, 3I Atlas was not merely a comet, but a messenger carrying information about hidden forces shaping the solar system in ways humanity had never before detected. The comet's tail, too, offered endless intrigue. Fragmented streams of dust and ionized gas shifted and reformed in response to solar-wind interactions, yet patterns occasionally appeared that defied conventional explanations. Some streams curved ahead of the nucleus, while others branched into fractal-like structures, as if the comet were leaving coded signatures in its wake. Scientists speculated that these patterns might provide clues to the internal processes driving orbital deviations, yet no model could fully replicate them. Each observation deepened the mystery, sustaining a tension between what was known and what remained hidden. As centuries unfolded in simulations, the long-term consequences of 3I Atlas's behavior became increasingly compelling. In some scenarios, the comet's orbit stabilized in the outer solar system, quietly retreating beyond the reach of planetary influence. In others, interactions with Jupiter, Saturn, and even Uranus created complex resonances that could send it veering toward the inner planets after millennia. While the likelihood of a collision with Earth remained extremely low, the mere possibility added an element of cosmic suspense, highlighting how seemingly minor orbital shifts could ripple across vast scales of time and space. Throughout these developments, the comet retained its enigmatic allure. It challenged assumptions, inspired innovation, and forced the scientific community to reconsider the dynamics of small bodies. 3I Atlas had become a symbol of uncertainty in a universe often modeled as predictable. Its journey reminded humanity that the universe is dynamic, that even objects following ancient Keplerian paths can surprise observers, and that scientific understanding is an evolving narrative shaped by the mysteries nature presents. And even as it faded into the distant Kuiper Belt, 3I Atlas left a profound legacy. It had reshaped models of cometary motion, stimulated new methods of observational astronomy, and opened a window onto fundamental questions about the structure and forces of the solar system. Its altered orbit, mysterious internal processes, and unexpected behavior had transformed a single icy body into a cosmic enigma, a puzzle whose resolution might take centuries, yet whose study had already expanded the horizons of human knowledge. And in the quiet of observatories, across telescopes both ground-based and in space, the central question lingered. What had truly caused 3I Atlas to change course after perihelion? Was it an internal mechanism, a hidden cosmic influence, or a combination of forces that science had yet to understand? The comet's secrets remained intact, silently journeying onward, and the universe, vast and indifferent, held its answer just beyond humanity's reach. In the end, 3I Atlas was more than a comet. It was a reminder that the universe is not merely a collection of predictable paths and immutable laws, but a dynamic, living environment where the smallest bodies can hold the greatest mysteries, and where the quest for understanding is an unending, thrilling pursuit. Its story, shrouded in intrigue and unresolved questions, would continue to inspire generations of scientists, dreamers, and observers who would watch the sky, wondering when and how the next cosmic puzzle would reveal itself.